So in this class we will study about single stage transistor amplifier. Okay, so why single stage? In single stage we are generally using a single transistor along with the associated circuits for amplifying weak signal. Okay, so a single stage transistor amplifier, it will amplify weak signal and it consists of a single transistor with associated network. So associated network means that it will contain the biasing circuit. Okay, so in any amplifier circuit, what are the things that are required? First is biasing circuit, then some passive components, okay, and the input signal. That we want to amplify. Okay, so this input signal, suppose we want to amplify it, so we have to use biasing circuit, passive component. Generally passive component we will be using only the capacitor, okay, and input signal. Okay, so we can design a single stage transistor amplifier like this. This is R1, this is R2, and this is RC, and this is RE. Okay, so this is a biasing circuit. Which type of biasing circuit? It is voltage divider biasing circuit. In almost all the transistor amplifier, we are generally using voltage divider biasing. Voltage divider bias circuit. Okay, why we are using voltage divider bias circuit? Because in voltage divider bias circuit, the operating point, that is IC and VCEQ, ICQ and VCEQ, the operating points are almost independent of beta. In previous class we have seen that if beta changes, then ICQ and VCEQ, it changes very slightly, almost negligible. Okay, so we are generally using voltage divider bias circuit in designing any amplifier circuit, because here IC and VCE both are almost independent of beta. Okay, so this is voltage divider biasing circuit. Then what we have to use? One capacitor like this. Suppose this is coupling capacitor 1. This is V in. This is emitter bypass capacitor. This is RL, and this is again coupling capacitor 2. Okay, so this is the circuit diagram of a single stage transistor amplifier. Okay, so this is biasing circuit and three capacitors: coupling capacitor 1, coupling capacitor 2, and emitter bypass capacitor. These three capacitors are added additionally. Okay, so how it works we can see. So what is the function of this coupling capacitor and emitter bypass capacitor? Suppose this is CC1 and CC2, both are coupling capacitor. And CE, it is emitter bypass capacitor. this is the input voltage, AC input voltage that we want to amplify. Okay, this is input signal, that is AC input signal. Okay, now the main function of coupling capacitor, it couples the AC input signal, to the base of this transistor. Suppose this is base and this terminal is emitter terminal and this terminal is collector terminal. So what is the function of any capacitor? It passes the AC and it blocks the DC. It will pass the AC input signal and the AC input signal will reach to the base of this transistor. Okay, that is why it is known as also coupling. That is, it will couple the AC input signal to the base of this transistor. Okay, and what is the use of this coupling capacitor 2? Okay, coupling capacitor 2, again it can be used for coupling various single stage amplifier to make it a multi-stage amplifier first. Okay, and also it will not allow to pass the any DC current across this. Okay, so no any DC signal will pass across this coupling capacitor 2. Okay, and it also provides isolation between suppose this is the first stage and suppose we want to design a multi-stage amplifier by coupling various single stage amplifier. Okay, so in between the two single stage amplifier, coupling capacitor, this coupling capacitor, it provides isolation between the DC resistance. See, in the second case it will be suppose R1, again R1, RC, R2 and RE, it will be the same diagram. Okay, so it will be coupled by this coupling capacitor, and if this coupling capacitor is not present, then what will happen? Then RC, it will be directly connected to R1. So this will affect the operating point, this will affect the biasing condition of the next stage of the amplifier. Okay, so generally we are using coupling capacitors first. Why? First to couple the AC signal only and it will block the DC signal. Okay, and second is it provides isolation. It provides the isolation between the DC resistance and this network. Okay, so coupling capacitor, it can also, this CC2, it is used for, generally it can be used for coupling several single stage amplifier to make it a multi-stage amplifier. Okay, so this is the use of coupling capacitor. Why we are coupling various single stage amplifier? Suppose this is first single stage amplifier, this is second single stage amplifier, and this is third single stage amplifier. Suppose the voltage gain, it is AB1 and it is AB2 and it is AB3 for the third single stage amplifier. Suppose this is V out and say this is V in. So why we want to couple various single stage amplifier? In order to increase the voltage gain. So overall voltage gain, it is V out by V in, that is AC V out divided by AC V in. It is equal to, it will be multiplication of all the individual voltage gain of single stage amplifier. Okay, that is why we are using multi-stage amplifier in order to increase the gain. In order to increase the gain means in order to increase the voltage gain, that is V out divided by V in. So it is equal to multiplication of individual voltage gain of each single stage amplifier. Okay, now we have to see the application of emitter bypass capacitor. what is the application of emitter bypass capacitor? See, the emitter bypass capacitor, it will bypass any AC voltage that will develop across this RE. So IE, the AC emitter current that will flow across RE, it will be bypassed. It will be bypassed through CE, through this coupling capacitor. Okay. So if coupling capacitor is not present, then what will happen? It will affect the overall voltage gain. So we will see. That reduction in voltage, output voltage. We will see reduction in output voltage if CE is not present. Okay, so this is the application of CE, to bypass any AC current that will flow across RE. So it is bypassed by using emitter bypass capacitor. Okay, and in general XCE, it should be less than or equal to RE by 10. It means that the reactance of this capacitor, it should be less than or equal to the resistance of this divided by 10. This we are taking the reactance like this. Okay, so we have to choose the capacitor whose reactance, it should be less than or equal to RE by 10. Okay, and here the BJT is used in common emitter mode. Okay, so how it amplifies? See, the AC input signal, it is passed, it is coupled by using this coupling capacitor to the base of this transistor. So IB is the input current, and output current IC, it is equal to beta times IB. Generally beta of this transistor, it is in the range of 20 to 500. So suppose if beta is equal to 100, we are choosing a transistor, BJT transistor, whose beta is 100. So it will be 100 times that of the input current. So this is IC. Okay. So in this way the signal is amplified. Okay. And here we are seeing that the phase difference between the input signal and the output signal. Suppose the VI. This is VI, and so V output, it will be like this. Phase shift, it is equal to 180 degree. In common emitter mode, the phase shift is 180 degree, so it will be amplified like this. Okay, so this is all about single stage transistor amplifier. Okay, now we will see, suppose for DC analysis, we can write IE, IB and IC. Okay, IE is the DC emitter current, DC base current and DC collector current. Similarly, for AC analysis, we can write IE, IB and IC. Okay, so these are the AC emitter current, AC base current and AC collector current. Okay, now first of all, in order to determine the Q point, how we can determine the Q point? Q point is generally determined under no any input signal. So this input signal, it has to be removed. Okay, so for this biasing network, we have to determine the Q point. Okay, so for determining this Q point, we have to use IC, IB and IE. All are DC currents. Okay. Then for AC analysis, when input signal is present, when input signal is given, then in that case IE, IB and IC, these are all AC currents. So the total IE, it will be equal to IE plus IE. This is due to AC and this is due to DC component. So this is the total emitter current. Similarly, we can write IB, it is the total base current, so it is equal to IB plus IB. This is AC component and this is DC component. Similarly, IC, it is equal to IC plus IC. This is AC component and this is DC component. So the total, this is the total current, total base current, total emitter current and total collector current. Okay. So in this way we can determine these values. Now we have to analyze this single stage transistor amplifier. Okay. So in order to analyze this amplifier circuit, we have to represent this in first DC analysis and second one is AC analysis. So in order to analyze this amplifier circuit, we have to do first DC analysis of this circuit and then second we have to do AC analysis of this circuit. Okay. So first of all, how we can do DC analysis for this circuit? Okay. So DC analysis, in DC analysis what we are doing? First AC input signal it has to be made to 0. It has to be removed. Second, all the capacitors it has to be removed or open. Okay. So in DC analysis, this circuit can be analyzed based on DC analysis like this. In DC analysis, what we have to do? We have to first remove this AC input signal or AC input source, it has to be removed. Okay. Then all the capacitors, that is CC1, CC2 and CE, it has to be removed. Okay. So this is all about DC analysis. Then second, about AC analysis. AC analysis, how we can perform AC analysis? In AC analysis, first of all the DC source has to be reduced to 0. Okay. So here VCC, it has to be connected to ground. Okay. And second, all the capacitors have to be sorted. All the capacitors, it has to be sorted in AC analysis. And all the DC, here DC signal is only VCC. So we have to remove this VCC and we have to put ground. Okay, analyze this circuit like this. Here it is VCC, okay, and it is, see, in DC analysis this is open, so this will be open, okay, and this is also open. Okay, and it is connected to ground. this is R1, this is R2, and this is RC, and this is RE. Okay, so this is all about DC analysis. So how to plot the DC load line? DC load line, it can be plotted like this. It is VCE versus IC. This is DC load line. Okay, so DC load line, it is VCC, and here it is VCC divided by RC plus RE. So how we can get these values? Okay, so in previous class also we have seen for a voltage divider, this is a voltage divider biasing circuit. Okay, in voltage divider biasing circuit, we can write down the equation for VCE like this. VCC, it is equal to IC RC plus VCE plus IE RE. You can write like this. Okay, and since IE is equal to IC, so we can write like this also. So from this we can write IC RC plus RE plus VCE. So in this axis, here IC is equal to 0. So VCE is equal to VCC. So this point we can get. Now along this axis, in this axis, okay, in this axis VCE is equal to 0. Okay, so if VCE is equal to 0, IC is equal to VCC by RC plus RE. It is VCC by RC plus RE if VCE is equal to 0. And here VCE, in this axis, VCE is equal to 0. So we are getting these 2 points. So we have to connect these 2 points. So this is DC load line. Okay, and the output characteristics, it is like this. Say this is IB1, IB2 and IB3, and this is IB4. Okay, suppose we are choosing value, we are choosing the value of IB, that is base current, equal to IB3. So the Q point, it will lie here, means the intersection of this load line and the output characteristic curve. So if we are choosing IB3 as the base current, so in that case ICQ and VCEQ, it will be determined graphically like this. This is the value of VCEQ and this is the value of ICQ. Okay, so in this way we can determine the operating point under no input signal, means when AC input signal is absent, then by using DC analysis we can determine the Q point and also the DC load line. Okay, so this is all about DC analysis of this single stage transistor amplifier. Okay, then we will see its AC analysis. So in AC analysis, how we can represent this transistor amplifier circuit from AC analysis. Okay, this can be represented like this. All the capacitors, it has to be sorted, and this VCC, it has to be removed, and we have to put ground in place of VCC. So the circuit will look like this. this is R1, this is R2, this is RC, and this is RL, and all are connected to ground. See, this is AC input signal. This is sorted. In AC analysis, all the capacitors has to be sorted. So this is sorted. Okay. Now this R1 and R2 both are in parallel. Why it is in parallel? Because now it has VCC is removed and it is connected to ground. So R1 and R2 both are in parallel. Then this transistor, then this RE, it is removed because this coupling capacitor, now it is like this, it is sorted. So RE is removed. Okay. Now this coupling capacitor, it is replaced with sort. Okay. And so RC and RL both are in parallel. Okay. So we are getting V output across RL. So what is the use of AC analysis? So we are performing AC analysis in order to determine the voltage gain. See, voltage gain, what is voltage gain? Voltage gain is output AC voltage divided by input AC voltage. Okay. So all are in AC. All the signals are AC. Output signal is also AC and input signal is also AC. So voltage gain we can determine like this. Okay. So this is all about AC analysis. So how we can plot AC load line? Okay. So we have seen, just now we have seen about DC load line. Suppose it is VCC and here it is VCE and this is IC. So it is VCC divided by RC plus RE. Okay. And suppose this is IB, okay, and suppose this is the Q point. Okay. So this is VCEQ and this is ICQ. So by using DC analysis we can determine ICQ and VCEQ, that is the operating point when no any AC input signal is applied. So we can determine the operating point by using DC analysis. This is DC load line. This is DC load line. So how we can draw the AC load line? So AC load line, for determining AC load line we have to draw another line and its slope, and it will pass through this Q point, and the slope of this line, slope it is equal to minus 1 by RAC, that is it is equal to tan theta. Where what is theta? This is theta. So the slope of this is AC load line. AC load line. How we can plot the AC load line? We can plot the AC load line like this. The slope of this line, it is equal to minus 1 by RAC. Okay, and it should pass through this Q point, earlier Q point, through this operating point. So what is RAC? RAC, it is equal to AC resistance. It is AC output resistance it is equal to RC in parallel with RL. RC in parallel with RL. And what is RDC? That is DC resistance. It is equal to RC plus RE. RC plus RE, it is the DC resistance. What is AC resistance? AC resistance is RC in parallel with RL. RC, this is RC and this is RL. So RC in parallel with RL, it is the AC resistance. Okay. So in this way we can determine the AC load line. Okay. So what is this? How we can determine this point and this point? Okay. Suppose this point is A, this point is say B. So how we can determine? We have plotted the AC load line, but how we can determine this point and this point? So point A, suppose this OA. So OA, it is equal to what? OA, it is equal to this VCEQ plus ICEQ into RAC. This point OA. Okay, and now this point OB. How we can determine OB? OB, it is equal to ICQ plus this ICQ plus VCEQ divided by RAC. Okay, so here RAC, it is equal to RC in parallel with RL. So in this way we can determine the AC load line and this value and this value also. Okay, so this is all about DC load line analysis and AC load line analysis. Okay, AC analysis and DC analysis. So we can determine the voltage gain, the current gain, input resistance, output resistance and power gain by using AC analysis. Okay, by using AC analysis of the amplifier circuit. Okay. So suppose the same amplifier circuit is like this. This is RL, this is coupling capacitor 2, this is RE and emitter bypass capacitor. This is R1 and this is R2 and this is coupling capacitor 1. This is V in. Okay. So how we can determine the voltage gain? AV. It is equal to output voltage divided by input voltage. Okay, output voltage divided by input voltage. So output voltage, it is equal to IC into RAC divided by input voltage, it is IB into Rin. So Rin is the input resistance of this amplifier circuit. ZRAC, it is the output resistance of this amplifier circuit. Okay, so what is Rin? Rin, it will be equal to R1 in parallel with R2, because in AC analysis it is R1 in parallel with R2 in parallel Ri. This is base and emitter which is in forward bias. So in forward bias Ri is very small. Okay, so what is Ri? Ri is the input resistance of the base emitter junction in forward bias condition. Okay, so we can determine in this way, we can determine Rin. And how we can determine RAC? RAC, it is equal to again RO in parallel with RC in parallel with RL. RO is the output resistance of this BJT, okay, and RC and RL. This is RC and this is RL. Okay, so in common emitter, we have seen in common emitter BJT, it has very low input resistance and very high output resistance. Okay, and in case of common